Good morning, everybody. Today we are going to be talking through Chapter 17. Which deals with aromaticity. We're going to start off with just talking through some common names of benzene-related structures. So things I'm going to refer to a lot. So generally speaking, 6-1 ring with 3 double bonds on it is benzene. If we add a substituent to it, such as like a halogen, so if you have like a fluorine, a chlorine, a bromine, or an iodine, you just add the name in front of it. So this would be chlorobenzene. Oops. Yeah. Nitro groups are kind of the same. So if we have an NO2, which is something we're going to be adding a lot, you would just call this nitrobenzene. And then carbon groups larger than 1 also just get their first name. So for instance, 2 carbons here, we just call this ethylbenzene. All right. If we just have 1 carbon, this is referred to as toluene. If we have an OH, this is phenol. A methyl ether is anisole. This one's probably one that we're not going to talk about much. NH2 is aniline. If we have benzoic acid, or sorry, if we have a carboxylic acid, it's referred to as benzoic acid. And the last one I'm going to talk about would be an aldehyde, and this is going to be benzaldehyde. So just kind of common names, things you're going to hear throughout the next chapter or two. 17 and 18 are very aromatic heavy. If you hear me referring to something as toluene, you know that I was talking about this versus like aniline, benzoic acid kind of a thing. These are probably names you've heard over if you've taken the lab or if just over the years, but just to give you guys a list of them. All right, so we are going to spend a good amount of time talking about what is an aromatic structure. Oh, yes, okay. And then we're going to do a little bit of, it's not quite naming, but we're going to talk about what happens if you combine these two together and talk about positions on your aromatic ring. So for benzene has, or let's take toluene. Toluene has 3 different positions on it because of symmetry. We have the position that is 1 carbon away. This is going to be referred to as the ortho position. And if, for instance, you had a toluene with a chlorine on it in that ortho position, we would call this ortho chlorotoluene, or you could just write it as O chlorotoluene. Our next position, which is 2 carbons away, still symmetrical. There's still 2 of them. This is referred to as the meta position. So, same concept. This is metachlorotoluene. Our last position is the para position. Oops. Or p-chlorotoluene. So there are 2 orthos because of symmetry, 2 metas because of symmetry, and then 1 para. Oops. We'll kind of review this a little bit more as we get into chapter 18, but it's something you're going to see a lot over the next, I don't know, I guess 2 or 3 days. So let's talk a little bit about what makes a compound aromatic. So benzene is usually our like standard for an aromatic compound. It is going to meet all of the requirements. So the first requirement is going to need to be that it needs to be fully conjugated. So what is meant by that is that you need to have a pi orbital in every position on your ring here. So versus something like this here, where we have an sp3 center. The sp3 center doesn't have any sort of pi orbitals in that particular position. So unlike with our aromatic ring, we can do something where we can just do resonance basically forever. So we can move these electrons counterclockwise. And then we could do it again. And again. And so on forever. Because we have this fully conjugated system, you can just constantly move your electrons around your ring. But because we have an sp3 center here, you can't do any sort of resonance. Besides just like this would be your full resonance structure. So we would call this non-aromatic, which literally just means that it's not aromatic. So that brings us to the second thing that needs to be, it needs to be cyclic. So something can be fully conjugated at every position. For instance, this here, it has 6 double bonds. Every single position has a pi orbital. But you don't have that like cyclic system where you're constantly moving the electrons around forever. Your only real resonance structures are, again, kind of the same thing. We're pushing these electrons to one side. So it has to be cyclic, has to be fully conjugated. Let's take a look at some interesting examples. There's one last rule we're going to talk about in a minute. Which is going to be clarifying whether something is aromatic or what we're going to call anti-aromatic. Okay. So if we look at this 7-membered ring with a plus sign on it, the plus on this center is still sp2, which means that there is a pi orbital at every position. We wanted to think of this like we were doing orbitals before. There's no heat or light, so they're just all going to be at the top here. You would have full orbitals everywhere, and then because you had a plus sign, this one's just going to be empty. So there's no reason why your electrons can't move freely through every single position in these rings. Because you are, one, fully conjugated, you have a pi orbital there. Even though it's empty, it's still there. And you're cyclic. So this here can do resonance kind of infinitely. We can move. Now our plus is here. And eventually we're going to be able to move through every single position in this ring. Oops. So on and so forth. Eventually you'll have 7 different resonance structures for this compound. Alternatively, you could also have a negative charge. So let's take the same thing. A negative charge is a full orbital. So we still have a pi orbital at every single position here. And we can also do resonance structures throughout them. This is actually what's going to be referred to as anti-aromatic, and we'll talk about that in a minute. Or actually, let's talk about that now. No, let's do it now. Okay. So there's 2 different possibilities. It's going to depend on your number of electrons in your system. So let's take a look at these 2 rings here. So let's write these down. Our last rule for something to be aromatic is has to follow the Huckel rule. Which is that it needs to fall into the category of 4n plus 2 electrons. So 4n plus 2 this is going to give us all the different possibilities of what can be aromatic. If we're just plugging in numbers, so if n was to equal 0, I'm just going to kind of go through them. So if it at n equals 0, this would have 2 pi electrons, 1, so 4, 1 times 4 plus 2, 6. 2 times 4 is 8, plus 2 is 10. 3 times 4 is 12, plus 2 is 14. 18, 22, 26, etc. These are going to give us all of our aromatic compounds. Nope, that's not spell compounds. Alternatively, all of the anti-aromatic compounds are going to fall into a 4n rule. So if n was to equal 0, well, we'd have 0 electrons, although that one doesn't really count. Let's start with 1 on this. So you're having 4 pi electrons, 8, 12, 16, 20, etc. N is not going to like correspond to a specific thing, like your number of double bonds isn't going to equal n. You're just kind of looking at the total number of pi electrons and then seeing which of the two categories it fits into. So taking a look at this top example here, we have 2 double bonds, and each double bond is going to correspond to 2 electrons. We have 1 positive charge, just nothing. Can you give us 0 pi electrons? Still important, but it is there. And we have negative charges, which are also going to be worth 2 pi electrons. So if we look at our structure on the left here, we've got 2 double bonds, 1 positive charge, which counts for nothing. So 2 times 2 pi electrons, this will give us a total of 4 pi electrons for the structure. If we go down to our little chart we made down at the bottom, 4 pi electrons falls here in the anti-aromatic category, making this anti-aromatic. And I'll give you a little bit more of a description of what that means in a minute. Versus on the right over here, we've got still 2 double bonds. We also have 1 negative charge. The 2 double bonds are both worth 2 pi electrons, so a total of 4 pi electrons from those, plus another 2 electrons from the negative charge, giving us a total of 6 pi electrons. Looking down at our charts here, 6 is going to fall into this aromatic range, and this will instead be an aromatic compound. I'm going to give you guys a minute to write this down, and then we'll talk through really what an anti-aromatic compound is versus an aromatic one. There's a question in the chat. So N, what does N stand for? Yeah, this is something that gets asked a lot. It doesn't really relate to like your number of double bonds or your anything. It's really just kind of like you're determining whether or not your number of pi electrons is either going to equal 4n plus 2 or 4n. Because it can either be, it can always be, it's always like a multiple of 2. So for this compound here, because we have 6 pi electrons. If you tried to solve for this anti-aromatic compound, so 6 equals 4n, you'd get a, I don't know, what do you get, 2.5? Which is not going to give you an integer, versus solving for 4n plus 2 would give you a value of 1, which is like an actual integer. I don't know, it's kind of a confusing rule, and a lot of people ask questions about this. Really, you're just kind of you're figuring out the number of pi electrons, and then you're just going to try to fit into one of these two equations. So it'll either have one of these values or one of these values here. And if it has one of the values in this like 2, 6, 10, 14 range, it's going to be aromatic, versus if it's in this 4, 8, 12 range, it's going to be anti-aromatic. The more we do these, the more they'll start to make sense as to what the actual 4n plus 2 rule really relates to. But it is a little bit confusing when you're first starting out. All right. So taking a further look at these compounds, I don't want the positive charge right here. So an aromatic compound is going to be highly stable, and for the most part unreactive. As we'll talk about later, you can't just like throw an H2 and reduce them. They're very stable compounds. Alternatively, the anti-aromatic ones are going to be highly reactive and unstable. Oh, these are also planar. These are also planar, but they'll want to contort to be not aromatic or anti-aromatic. So what makes something aromatic versus anti-aromatic is going to have to do with its pi orbital bonding. If we think back to like orbital bonding, so let's take this compound here. If we're looking at just its pi orbital, you would say that there's, you guys probably did these bonding structures a long time ago. We've got 2 pi electrons. They are going to fall into this bottom category in order to create a bond. When we do this for a cyclic system, we're going to use what's called the point rule, where your number of the size of your ring is going to determine the number of orbitals you have. So here we have a 5-membered ring, and you're always going to have a pattern where you have 1 on the bottom, and then you'll have just kind of pairs until you hit another single or you run out of pairs. So if there's 5, it's a 5-member ring here. We'll have 5 bonding orbitals. I'll erase these real quick. So when we draw our pi bonding system, it's going to kind of look like a 5-member ring. You can kind of draw one in here. These are the 5 bonding orbitals. We'll do a 6-membered ring in a minute, and you'll see it also looks like a 6-membered ring. So we have 4 pi electrons. I'm going to draw 2 on each side. When we fill in our electrons for these, for anti-aromatic compounds, they're going to be unpaired at their highest energy orbital. Versus this other 6 pi electron system. Now we've got paired in our highest energy orbital, which is what makes this so stable. When we have these unpaired electrons, they're going to want to react as much as they can. So let's do one more of these frost circles and then just start talking through examples. So a 6-membered ring. Let's take benzene here. Its pi orbital bonding system is going to look like a 6-membered ring. So we're going to have 1 by itself on the bottom. These will be our 6 pi orbitals. It's a 6-membered ring. You always have a 1 on its own by the bottom. You can kind of draw in an actual 6-membered ring if you want. Oops. We have 3 double bonds, which means we have 6 pi electrons. And we're going to be paired. We have a 7-membered ring. Put a negative on it. And then we have 3 double bonds. 1 pi, or what? Sorry, 1 lone pair. So we have a total of 8 pi electrons. We need 7 orbital levels because we have a 7-membered ring. So 1 by itself. 1 pair of 2, 2 pairs of 2, 3 pairs of 2. We're filling in 8 pi electrons. These are now unpaired at the top. this would be anti-aromatic. And this is going to be aromatic. It's kind of a way of representing that like Huckel 4n+2 rule. A lot of the time we're just going to use identifying the number of electrons and say whether it fits into our 4n+2 or the 4n rule. So if I write those out again, our aromatic compounds are all going to be this either 2 pi electrons, 6, 10, 14, 18, 22 category. Our anti-aromatics would be 4, 8, 12, 16, 20. Looking at these compounds, we had 6 pi electrons. This fits into our Huckel rule. We'd say this is aromatic. Or 8 pi electrons, it doesn't fit into this one, it fits over here. And this is anti. Okay, one more concept we're going to talk about is heteroatoms of these. And this is going to deal with localized versus delocalized electrons. So this nitrogen here has what's referred to as delocalized electrons. They can partake in resonance. So when we're calculating the number of pi electrons in this system, we are going to count our delocalized electrons, similar to how we would count a negative charge. So because I can take these and move them around my ring as much as I want to, we're going to consider this as having 2 pairs of double bonds and 1 lone pair. So this would have a total of 6 pi electrons. A good rule of thumb is that if your lone pair does not have a double bond attached to it, it's going to be delocalized. Versus something like pyridine, where these 2 electrons are localized. They can't partake in any sort of resonance. They also have a double bond attached to them. It's right here. It's currently attached to them. This, on the other hand, just has a bunch of single bonds attached to it. So when we're determining our pi electrons for this system, we would not count the localized electrons. We would say this has 3 double bonds, and therefore 6 pi electrons. 6 falls into our Huckel rule of 4n+2. It's where n would equal 1. So these are both aromatic compounds. A good example of when something is a localized versus delocalized is going to be oxygen in one of these rings. So if I have this furan ring here, I've got two different sets of lone pairs. One of them is going to be localized and one of them is going to be delocalized. Doesn't really matter which pair you pick. I mean, they're kind of moving around, but if we think of this as our rules here, currently there is no double bond. So we would say that they are delocalized. When we do resonance, now there is a double bond attached to that oxygen. So we would say that this one that we moved was a delocalized pair. But our other set of lone pairs is going to be localized. Because now it already has a double bond onto it, it can't move again. So when we're counting lone pairs from this system, we say that only one of them is delocalized. So this is, again, 2 pi electrons, or 2 double bonds, and 1 lone pair. If we put this into a larger system, a little prettier. We could use that concept again. So each of these oxygens has the ability to donate 1 set of pi electrons into their system. Just drawing out some resonance structures. So when we think of these here, we would say that there are 2 double bonds in the system. And then each of these oxygen has the ability to have 1 set of localized lone pairs. So there's 2 sets of lone pairs, 1 for each oxygen. This is going to give us a total of 8 pi electrons. That's a 4. So now when we try to plug this into our Huckel rule, 8 isn't one of the options. It's only 2, 6, 10, 14, etc. So this one is going to be considered anti-aromatic. Okay, let's take about 6 minutes, about a 6-minute break. Let's do a 7-minute break. So we'll come back at 10:07, and then we're gonna do a bunch of examples. I'm gonna give you guys, like, I don't know, 4 or 5 compounds to go through and try to identify whether they're aromatic or anti-aromatic. And then we'll talk about a couple of reactions that deal with this. Mostly just like reducing and stuff like that. Tomorrow will be the like big aromatic reactions day. So meet back here at 10:07, and then we will talk through some more of these. All right, so take about, I'm gonna give you guys about 5 minutes to go through these. Try to figure out if they're aromatic or anti-aromatic. So count your electrons, see which of the two rows it fits into. For these like larger systems, treat it like it's all one big pi electron system. So count the total number of electrons in your system and just act like it's a normal single ring system, even though it's multiple. All right. Gonna write out your rules down at the bottom. So we'll be back here around 10:14 to talk through these. All right, so let's start taking a look at these. Our first one, we have one double bond. And a positive charge. So this would have a total of 2 pi electrons. If we look down at our two different charts here, aromatic has 2 pi electrons. So this should be an aromatic compound. For our next one, we have a nitrogen that doesn't have any double bonds attached to it, so its lone pair are going to be delocalized. Same thing in the oxygen. We're going to end up with only one pair of delocalized in the oxygen. Once you do resonance, the other pair will be localized. And draw the localized ones in green, the delocalized ones in blue. It's going to give us a total of 2 double bonds. And then 2 sets of lone pairs. So we give us a total of 8 pi electrons, which falls into our anti-aromatic category. All right, we have an oxygen with a double bond already. So its lone pairs are going to be localized. We got a negative charge. Let's see. So we have 3 double bonds. And 1 lone pair for this negative charge. Giving us a total of 8 pi electrons. Same as the last one, 8 falls into our anti-aromatic category. Down at the bottom, our nitrogen already has a double bond, so these are going to be localized lone pairs. We're going to have a total of 1, 2, 3, 4, 5 double bonds on it. Positive doesn't count for anything, so that's 10 pi electrons. 10's over here in aromatic. So this will be an aromatic compound. All right. We've got 1, 2, 3, 4, 5, 6 double bonds. 1 set of lone pairs from the negative. So that's a total of 14 pi electrons, which is over in our aromatic category. Any questions on these?
Excuse me, I have a questions about the lone pair. We just count the lone pair as the delocalized lone pair, right?
Yes. Only count the delocalized ones.
Thank you.
You're welcome. Okay, I'm going to give you guys actually a few more of these. Just to do them, and then we will move on to some reactions. So we're going to do about, let's say, 4 more of them. Maybe 3 more. So do these last three. I'll give you guys till about 10:22, and then we will go through them together. All right, so all of our lone pairs on the right are going to be delocalized. They already have a double bond to them. The ones on the left here are going to be localized. So we'll count the ones in blue. So that's one set of lone pairs. And then we've got 1, 2, 3, 4 double bonds. Giving us a total of 10 pi electrons. Ooh, we lost our chart down to the bottom. Ten falls into our aromatic. Do these all fall into our aromatic category? That might all be aromatic. This falls into our aromatic category. The next one we have 1, 2, 3, 4, 5, 6, 7, 8. Ooh, good. Double bonds. This is going to give us 16 pi electrons, which would be over in our anti-aromatic. Lastly, let's see, 1, 2, 3, 4, 5, 6, 7 pi electrons. Or sorry, 7 double bonds. So 14 pi electrons. Making this aromatic. Okay, so that's kind of aromatic versus anti-aromatic. We'll do a little bit more of this in recitation today. Let's talk about some reactions. So a lot of these reactions are going to be somewhat review. We're going to start off with one that's interesting. If you take toluene and you throw in our strong oxidizing reagent. This will, even though there's no oxygen on there, it's still going to oxidize it all the way to a carboxylic acid. Has to do with the aromatic properties of it. The interesting thing about this reaction is it will actually oxidize anything to a benzoic acid. So it's so strong, it's going to end up breaking carbon-carbon bonds here. So this will actually completely break down. It's going to cleave the bonds and form benzoic acid. If we have a couple of different substituents on here, every position is going to end up getting a carboxylic acid on it. And breaking off any other carbons it happens to have on it. We can also do this with KMNO4. It'll do the exact same thing. So if you add in just a different set of reagents, it does the same reaction. So KMNO4 and H2O and heat, followed by H3O plus, will also give you this. And then if you have multiple of them, it'll break apart things and do the same concept. So anything chromic acid does, KMNO4 will also do. What happens to the cleaved carbon chains? They're honestly just like kind of floating around in solution. You're not really caring about them, generally speaking. I think they will eventually oxidize to carboxylic acids in those positions. The only time that this doesn't work is if you have a tert butyl. You need to have at least one proton there to pull off to initiate the reaction. Let's say you had a methyl and a tert butyl. It'll only react on the methyl side. So kind of an odd reaction. Not a lot of reactions allow you to burn off carbons, but this one does. All right, another reaction that is, I guess, not similar. So this is a reaction we've done before. So if you had NBS to a compound with a double bond. This was back in chapter 10. We're able to brominate at the position next to our double bond. If we do this with an aromatic ring, we can also permanent next to the double bond, permanent next to our ring. So same kind of concept. If you have a terp butyl, it won't work. It has to have some sort of hydrogen to pull off. If you add a methyl and a terp butyl, it would only add the methyl. Nope, need a carbon there. Okay. So as we talked about a while ago, these aromatic rings are incredibly stable. If you do your normal reducing conditions, we throw in H2 and platinum. This is going to do nothing, actually. It's not strong enough to actually reduce these aromatic bonds. On the other hand, if you had something that was anti-aromatic, it's going to readily reduce it. We got 4 pi electrons here. It's going to fall into our anti category. Going to very quickly reduce down. We threw in the aromatic version of this. We get no reaction. Your book does mention that you can do this with if you add an H2 and nickel, 100 atmospheres of H2. And 150 degrees Celsius. Your book talks about it like it's a normal reaction. You have 100 atmospheres of pressure and 150 degrees Celsius. This is a massive bomb. This is not a reaction you actually want to do. This would most likely kill you. So there are ways to get around this. We are going to use radicals to throw more electrons into the system, and then we'll be able to reduce it. So kind of like the way we were reducing triple bonds, we're going to take sodium 0 again. So if we take a aromatic ring like benzene, throw in sodium and methanol and ammonia. This is going to donate 1 electron. So half arrow because we're donating one electron. We can have another electron come from our double bond here, kick an electron out. We would initially make this. This is really going to be a less favorable resonance structure because we have these two electrons sets that are next to each other. They're going to really try to repel each other. So what's going to happen is that they're just going to move to opposite ends of their structure. So these ones are going to move down. To generate this here. From this point, you can pick up a proton from, let's say, methanol or ammonia. We're going to throw another electron in here. That is not how we draw sodium. Pick up another proton. And we'll make this system where our double bonds are on either side. From here, you can throw an H2. It's not aromatic anymore. We got sp3 centers. And we can get down to cyclohexane. This is referred to as a Birch reduction. There's two different ways that can happen depending on what your substituents are on your aromatic ring. So we'll talk about those now. Okay, so let's talk about the two different possibilities. If you have a carbon coming off of your ring and you throw in Na, and we'll go through a mechanism in a minute, NaCH3OH, and ammonia, this is going to give you a double bond pattern where one of your double bonds is going to be on that methyl group and the other one is going to be adjacent. Alternatively, if we use something like benzaldehyde, we're going to end up with a different double bond pattern. Not what I want to write out. We're going to end up with a pattern where they are flanking each other. So neither of them are attached to where that aldehyde center is. They're instead on opposite ends. So let's start with the first one. It's really just going to have to do with double bond stability. So I'm going to erase the benzaldehyde example. We'll redraw that in a minute and go through that one. All right, so we're going to donate a single electron into our system. generate a negative and a radical, they are going to repel each other. And there are a couple of different resonance structures that can form. We could either have this resonance structure. I'm not going to draw out all the arrows to get to them. Or a resonance structure that looks like this. And you could switch where the radical and the negative charge are. It'll kind of give you the same thing. Either they're going to end up on the carbon with the methyl group on or one away. And if you kind of go around this ring, you'll find that they are symmetrical. So these are really the only two you could have. Technically, you could get like the opposite ones. So negative, single radical. That's wrong. And as we're looking at these, we're just going to deal with double bond stability. So this here is a tertiary double bond. Secondary one, tertiary, secondary, versus over here we have a bunch of secondaries. They all have two substituents off of them. Meaning that this set here is more stable. And therefore, this is going to lead us to our product. So in our first step, we'll pick up a proton. I'm just going to do the top part of it as the example. So this could pick up an H plus and something like methanol. We'll get another radical. This is yet again the most stable position. The reason for that is it has two resonance structures. It could either go here or here to get resonance, versus if you had it on one of the endpoints. The only resonance structure this could make would be going back the other direction, versus this one here where it could go in either direction. So that actually makes it a little bit more stable. So this will be considered our most stable resonance structure. And that's why this is going to lead to a product. Here are these little blue arrows. And draw this picking up an H plus. And that is why for these products, we end up with these double bonds where one of them is attached to our substituent and they're kind of flanking each other. Our benzaldehyde example follows similar rules. Except now when I add a sodium into the system, I add a single electron. This is going to go through resonance and end up orienting itself. It's going to want to put this negative charge in the position next to this benzaldehyde. The reason for that is it now has 3 different resonance structures. It could go over here, it could go over here, or it could go up onto your carbonyl. So it's even more stable than it was before. So being in this position, it's kind of like the most stable spot it can be. Oops. Oh, moving so many things. Now when it picks up a proton, it can follow the same rules as before. It's going to pick up another electron from sodium. It wants to stay in the middle here because that's going to have more resonance structures. We can pick up an H+. And now we get a different looking non-aromatic compound. All right, so not a ton of reactions from this chapter. Most of this is focusing on aromatic versus anti-aromatic. We throw in chromic acid or KMNO4. We can blitz this all the way through to a carboxylic acid. NBS lets us brominate. At this benzoic position. Throwing in H2 and platinum's going to do nothing. We need to use one of these Birch reductions. Followed by H2 in order to do this reduction here. And if we had something like benzaldehyde, we get a different pattern in terms of our reduction. If we throw an H2 here, we'd actually also reduce the alcohol. Going back to some chapter 12 reactions. This could take us all the way down to here. Okay, this is everything from chapter 17 we're to cover. Tomorrow we will start on chapter 18. We might spend 2 days on it. It's a little bit more complicated. We're going to deal with a bunch of different types of aromatic substitution reactions. So I will see you guys either in recitation today or tomorrow. Have a good rest of your Thursday.